So today's lecture is on resource management. It's mostly around what's actually going on under the hood when it comes to C++ and memory, things like malloc and free, moving and copying memory, a bit of background on how things like STL containers actually work. This lecture used to be quite pivotal for the previous assignment 2. This particular assignment 2 you have actually doesn't have you deal a lot with memory. So the assignment 2 that we used to run for a bunch of years, 19, 20, 21, and 22, after I was done with the course, it was all about creating it was like a Euclidean vector assignment. And what you did in that assignment was you basically had a vector, right? Like a literal array that you could do things like dot product and multiply and add and subtract. And what we made students do was actually malloc the underlying data as like a raw C-style array underneath, right? And that mallocing then meant you had to do a few things. It wasn't hard, but it definitely involved knowledge from this particular lecture. You're in luck that, as far as I know, unless I misunderstood something, this really doesn't have a huge amount of relevance to assignment 2, but it will have a lot of relevance to assignment 3, because in assignment 3, I believe you will be doing a little bit more that makes you think about how some of this stuff works. So, whilst we've ignored heap resources, when we say heap resources, we're talking about malloc and free to date. They're a critical part of many libraries. When you use something like a std vector or an std array or an std list, all of those things themselves are going to be actually mallocing memory, right? Like all the stuff you've been doing so far has just been memory on the stack, because obviously variables are all on the stack. But when you do a std vector, it is mallocing something. They're all mallocing things behind the scenes. They're just not showing it to you, because what happens when you malloc stuff is you have to deal with a pointer, and what happens when you deal with a pointer, you're probably going to shoot yourself in the foot, right? So that's why we have these nice abstracted libraries. So we'll be covering a few of these things here. Not going to be a massive lecture tonight either. Pretty cruisy till the end of term, if I can be honest. Also a reminder, we do have that guest lecture still in week 10, so make sure you continue to save the date. Yeah, I think I said that in week 1, but it's actually not at the standard time, so there's no point in me saying save the date, because he's doing it at a different time, and I haven't told anyone that yet, so I should probably tell you that first, and then you can save the date. But it's like 12 p.m. or something, pretty manageable. I will sort that out this week, actually. So quick bit of revision. What is an object in C++? It's like a struct with functions. It's a region of memory associated with a type. So anything as an object, things like ints and stuff can be treated like such. But all of these objects we deal with, they do need to be created, destroyed, copied, and moved, which is what today's a lot about. It's about what's going on under the hood with memory in relation to those things. Do you have a question?
In today, can't you also have functions within a struct, just like function pointers?
Yeah, of course.
So,
absolutely.
What's the actual fundamental difference in C++, really?
Between an object and a struct?
Is there something like extra that C++ is doing that makes it?
Not really. It's a great point. And I mean, I think what I'd reference is like the whole thing we talked about, how you can use the struct or class type, right? Because they are essentially the same. Like if you think about it, like a struct you could imagine as just a series of properties, and then the functions are just function pointers to something else. I would probably view the idea of a class, honestly, as just like a massively helpful piece of syntactic sugar that does that exact same thing. Because the struct is a type, and what you would do in, say, like a first year course is you would go and malloc a piece of memory the size of that struct, and then have to handle all the, where everything is. So it just makes your life easier. But yeah, you could imagine them as basically the same, for sure. I think, well, basically the same. You could imagine them as extremely similar, at least. I don't want to eat my words later. Yeah. I mean, you usually say that like you instantiate an object of that class type. So I mean, the same thing as with structs. When you could argue, I don't think I've used that language specifically, but when you malloc something associated with a struct, you are basically allocating memory of that particular type, and you could do that as many times as you want. Long lifetimes. What is it? I mean, we talked about lifetimes are associated with scope. The lifetime of a particular name in C++ is attached to the scope in which it's valid. There are 3 ways that you can try and make an object in C++ have a long lifetime. And a long lifetime is something that outlives the scope in which it was defined. So one of the ways is to return it out of a function by copy. That makes sense. If you have a function, just to make this really clear, make that smaller. You know, I've got my little int function, and all it's going to do for me is to create an int called a, and it's going to return a. So a has a scope that begins on line 2 and finishes on line 3. The lifetime of a, the name, is just those 2 lines. However, because I'm copying it out of the function, that particular value I have, it will have a lifetime that exists beyond its initial scope inside the function. So that's one way to do it. Obviously, we've been doing that since like week 1 of term 1 of year 1. Or we could return it out of the function via a reference. This is bad. What I mean by that is if you're like, I really want this a to last forever, but I don't want to copy anything or waste memory or performance, you say, aha, I'll just return it out of the function as a reference. Genius idea. That's bad, and we'll talk about that. Or you could return it as a heap object. And in C terms, just as a reminder, so you know what I'm talking about, remember heap objects are unnamed objects. Quick bit of revision, int star a equals malloc size of int. There's your malloc, and then you can return a if your function returns a pointer to an int. So again, remember, we call them unnamed. It is called unnamed memory because that doesn't have a name. A is a pointer to the thing that doesn't have a name. It's a bit tricky because you think, oh, its name is A. It's like, no, its name is not A. A is the thing pointing to that thing without a name, which therefore makes A the one managing that area. This works too. That's number 3 there. That's that explicit heap management part of things. So the heap is really how we get around lifetime problems with the stack. That's a great way to think about it, because the nice thing about the stack, as in variables and functions, is that it's just managed for you. You don't have to free anything. You can't forget about anything. It efficiently adds stuff, takes stuff off, adds stuff, takes stuff off. But you're then constrained by the scope, lifetime rules associated with it. This is like the older sibling version of it, where it sees like, I'll trust you, you do what you want, don't break anything along the way. So one of the problems though with returning references, and you can see some kind of examples here, is we need to be very careful when returning references. And that is that the object that we're referencing must always outlive the reference itself. And you can see here some examples at the bottom. These are okay because what we're doing is we are passing in a reference to an int into both of these functions, and then we're returning that same reference. Now this is okay because this particular function, it was created after the original int being passed in was defined, and it dies after that original int was there too. It's pretty intuitive, right? My words might even make it more confusing. But the one on the right here is what I was just talking about, where what these functions are trying to do is to return a reference to an int that was defined within the function. So in this particular case, if you have an int reference to that I variable here, the correct terminology is that reference will try and outlive, what do we use here? The reference will try and outlive the object that it's referencing. Now, it's important to note in the slides too, it says this is undefined behavior. Undefined behavior we chatted about a little bit earlier, but it doesn't strictly mean it's an error. It just means that it is not defined what's going to happen in that scenario. Anything could happen on a spectrum of a seg fault all the way through to the program functioning totally normally, right? And what's the seg fault situation? Well, it's when that reference is pointing to that original stack memory and something's changed there that just completely kills the process. The other one is that what was originally at that address in memory, because remember when you take things off the stack, it doesn't just wipe it, it's just sitting there, right? For as long as till something overrides it, is that it could just work totally fine. Because whilst your reference outlives the object, what it's actually referencing specifically in memory is still just sitting there waiting to be used. And undefined behavior errors are really tricky because they can work 10 times and then fail the 11th, and fail the 12th. Non-deterministic errors are terrifying errors. And if you start working with a big code base, you'll uncover that pain. I always like to tell people my favorite story was my favorite non-deterministic error story. And this one wasn't a particular problem in code. This was like me and my friends being mean to each other. I don't think I talked about it in this course, but there was the whole robot socket. I think I did because we showed the code for it. But one of the things we used to do to each other to prank each other was like we'd be writing code for these robots. And at the top of one file, there'd be like 1,000 files. We'd always have our little like hash define true as 1 and hash define false as 0, something like that. What happened is one of us would like leave the lab and go to the toilet, as you do, and the other one would kind of quickly dash over to the computer, and we'd usually replace this with like randint 01. So what would happen is every single time it would like run, true would be a different value of 1 or 0. And that's non-deterministic problems, right? So we usually let the other one try and figure out why the code doesn't work for about 5 minutes. We weren't too mean about it, just a little mean. Sorry?
Was that intended, or?
Yeah, we were trying to mess with each other. That was the point. I was saying this is another good example of like a non-deterministic error, or a non-reproducible error, right? Because when you deal with large code bases and someone has a problem, the very first thing you have to do is say, show me the exact steps how I can create that problem, and how if I do those steps 100 times out of 100 times, I'll get that problem as well. Because if you do that, you can mostly fix everything really quickly. But if you don't have that capability, then it's like hellish. So my point is undefined behavior is hellish like that, because it might work sometimes, just depending on what's going on with the particular memory.
What happens when you get 0 and 0 then?
Sorry?
What happens when you get 0 for true and 0 for false? I don't know.
Yeah, hell breaks loose. Like you're right. This is deterministic at compile time because like it compiles to a particular value. So if you take it literally, that makes sense. It was more that every time you. Oh no, this isn't at compile time because it just pastes it into the code. Yeah, exactly. So if you have like if a equals true, basically it'll just paste that in as like that. So every time you run it, it'll be different.
Const expression or something for that?
Yeah, you could. I think we covered that in week 8 a bit for those who aren't too sure. We're talking about const expression, little teaser. Yeah, very interesting stuff. So it's undefined behavior. I think we tried this out in a previous week. I don't know if someone remembers it. I don't remember if it worked or it didn't. Does anyone remember? I tried to do this back in week 2 or 3. Nah. Well, I guess we're going to have to find out again, aren't we? Let's find a random example. Still recovering from Monday, that horrible debugging moment we had. Let's just make sure this works for a sec. So, build, make, iterator, invalidate. What is it? My brain, IO stream. All right, 5.4.2. Iterator invalidate. Hi, cool. So what we were trying to do, we were trying to make a function, return an int reference, blah. It simply goes int a equals 5, return a, and then we want to print out the result of blah and see what happens. We're basically interested if the compiler will pick up on this. Now, I thought this was what happened. What you're seeing here is the compiler noticing the problem, right? It's picking up on that potential undefined behavior problem, but it's only doing it because of the warning return stack address flag on the compiler and the W error, which is convert warnings to errors flag. So what I mean by that is if I just went back up a folder into 4.2 here, and I just did like a real raw G++-O, or like don't even need that, just our like iterator invalidate. No, I still get that. Yeah, it's still a warning, so it still actually compiles. So you see here, like it's still working, but this is technically undefined behavior. The program is so simple that obviously nothing else happens on the stack. I'm sure that like, and I don't know here, but like, I'm sure if I had a global variable, it'd probably just give me a different problem. Yeah, I don't know. I don't want to go too deep into this, but if I had another function that goes and like makes another few variables here. Hello. So like what can happen then in this particular case is like, let's say I don't know, I say int a equals blah, and then I call blah 2. and then I do a here. In theory, we're going to start overriding the stack variables, maybe. I don't know. I don't spend a lot of my life kind of messing around with like really specific compiler problems, but yeah, see, clearly I don't fully understand it. But the point is that at some point, what it's referencing on the stack in terms of that return address is going to override it, right? Now, this could be fine most of the time. And realistically, for your programs, it usually is going to be fine because your programs are going to be pretty plain. But it's something that you should avoid doing. Thankfully, the compilers will pick up on it, as you've seen with the return address. So we really can stay away from it pretty comfortably. Not that you do that anyway, right? But it is kind of intuitive to some people to maybe want to return a reference to something you put on the stack. It's not to say that we can't return references to stack items. That's totally fine. It's to say that we can't return references to stack items where the reference is going to outlive the lifetime of the underlying object. Someone has asked on the chat, how about the lifetime of closure, like the predicate in assignment 2? I guess that's fine. I never really thought about that in terms of, I don't know. So the question that's been asked is a good question. Ugh. Sorry. I just want to have a quick look at the assignment 2 spec. No. So if we look at, that's a student's work. If we look at this, I really don't know the answer to it, but if we think about a predicate, I imagine that when a predicate's defined, I don't know how a predicate actually works, because I get a predicate, it's just a pointer to a function basically, right? Well, it's just a lambda. I'm not sure, maybe it's defined in code. I imagine it's probably similar to, you know when you do something like you say const char star s or something equals Hayden, like this. That like this is a string literal, which is different, right? Because like and this is very different. Like if I have something like this, right, and then I come along here and I say const char star s2 is an array of 6 items, something like that, and then I say s2 0 equals h. And then s2 1 equals a. And I do that for everything else, right? This one here is actually an array on the stack that contains those elements, right? All of those characters in that string. Whereas this one here is a string literal that's defined straight into the binary, typically, that it outputs. And if you're not too sure what I mean, usually I can probably show you that thing I mentioned in a previous week. We kind of looked at this a little bit back in week 2, or I can't remember if it was week 2 or something. Hopefully this works for me. But if we look at a really simple piece of code like this, so what happens here is that like this isn't actually something that is like stored on the stack strictly. That string literal is stored in the code itself, like directly in the compiled code, because it's a literal. And that means that come printing time, it can just print it straight out from code rather than having to store it in the stack. And again, that's a very different thing to if I was to go like S2, 3. Or say I just do H or something nice and easy. How do you make an array again? Oh, okay, sure. Because then if I say S2 0 equals H, why is it upset? Oh, sorry. Oh yeah, true. Good old C. That doesn't even make sense now. I was like, that didn't make sense in the first place. So like what's actually happening here in this particular case is like this first one, it's storing the actual string in the compiled code, whereas this one here, it's kind of saying that, hey, when the program runs, we're going to like move that to a particular memory address and stuff. Similarly, if you have like a really big, massive string, it'll actually just store that whole thing. So in a way, string literals, oddly enough, actually increase the size of the binary that you compile a lot of the time. Anyway, I don't even remember the purpose of that. The purpose of that was to say, I imagine to the question that predicates are probably stored in a similar way. I imagine, I don't know. So like if you define a function in your code like a predicate, it probably just stores it as binary code It's not really storing it in the stack or anything that you might be trying to imagine in that direction. So like a reference to it is just like a reference to a string literal. Because, to make a point here, if you have a function like this that, say, returns a char star called blah, and then you say char star s equals Hayden, and then you return s, or maybe actually let me make that whole thing like a... yeah, I mean, this isn't a great example because we're not using references. Sorry?
No, it's a pointer.
Yeah. My point here with this case, this is not my favorite example, but if you were to have a string like this and you were to return a reference to it, it doesn't matter because some things like string literals don't have a lifetime, is my point. That's probably the better way of explaining it. String literals don't have a lifetime because they're defined in the binary code. They're just referenced in the binary code. They don't exist and then disappear. They're just referenced there. And I imagine that predicates are the same thing. They're just functions, right? Because all your functions, like main and blah, are just referenced. They're just written into the binary code. So I don't think the question about lifetimes makes sense. But again, I'm not an expert on a lot of this. I'm doing my best to make sense of it. Tim's asked a question about, back to this, what was the example we had? I'm just bringing up an old example. So Tim has said, given that you wrote int a equals blah, sure, rather than int reference a equals blah, does that mean it would have been copied out? Oh, that's a good question. So if you have a piece of code like this, is a copied out or is it not copied out? I believe it's copied out, unless I'm missing something. Yeah. I guess by a similar measure, is that copying out too? This is trippy. I don't know. I feel like it's one of those obvious answers that's a bit too... I mean, does it compile? That's usually a good measure. I see the chat flashing. Where are we? Yeah, okay, that's yeah, okay. This is cool because we're talking about L values and R values. Because what I was thinking with this is that it's definitely copying it out of this function, right? Because like it's a function, it has to return an int and a copy of an int. But the problem is like what happens, imagine this function's called. Once it returns and is out of it, it's the equivalent then of writing this code. Because the 5 is copied out of it, which is fine. There's no issue with that. But then you're trying to say a is a reference to an integer. But the problem is a reference needs to be to something that has a memory address. So hold that thought, because we actually talk about this today, even though we're not moving very quick. So revisional objects, we already talked about that. Why do we need heap resources? I think we've kind of covered that in detail as well. The stack is also smaller. I don't think I kind of covered that. The stack's not very big in terms of the memory allocation. So you wouldn't go and create like a billion array item on the stack because it just isn't that large, whereas the heap is quite large. So we use the heap for things to outlive it. Yep. Cool. Now we're going to talk a little bit about what's going on with a standard vector of ints underneath the hood. So let's speculate about how a vector is implemented. I'm not going to be telling you this is strictly how it's implemented. I'm sure you could go look up the libraries for it, but it's more a conceptual understanding of it. A vector is going to have to manage some kind of heap memory. So if I gave you an assignment now and I said, I want you to make me a vector of ints class, you would probably make it look something like this. You would have a class called vector, whatever, and then you would store a few things. You would probably store a integer pointer to data, which is going to be an array of some sort. You're probably going to malloc something. Let me just make sure I didn't skip the malloc part. No, I didn't. It's going to malloc something. I'm going to have a destructor that does nothing, and then I need a size and capacity, right? The size I kind of need because it's a raw array, so I need to keep track of how many items are in it. And the capacity is the physical size of the memory, I guess. Sorry, the capacity is the size of the memory. The size is how many elements are in the array. So I would go and make something like this. Now, this piece of code obviously doesn't compile because it's a little bit BSy, but you will notice this little new part here. I think that during a revision of one of the lectures, Chris from Google was really big on not even actually really teaching people how to do new and delete, because then it might encourage them to use it when you kind of shouldn't. I think that makes a lot of sense generally. I think trying to understand it, I just want to kind of show you now. If you were writing a piece of code that created things on the heap, if you were doing this in C and you wanted to create an integer array of size 10, right? So imagine, you're doing something with a vector. It's int star data equals malloc size of int times 10, where 10 is the size of the array. And if you want to free that data, you do that immediately after. Sweet revision. That should work. C is backwards compatible with C++, but I would need to actually then include the C libraries, right? Which is standardlib.h, I guess. Right? Line 10. Oh. Sorry, good spot. Cannot initialize variable type int star with an R value type void star. Oh, is this that stupid thing we always have to do? No? Use of old star. Okay. We're snookered by the compiler. It won't let us do it, probably. Or I'm silly. But that doesn't matter, because we're not trying to do that. That's maybe how you do it in C. Point is, the thing I'm trying to get across is in C++, this is how you would do it. You would say data equals new, then I believe int 10. I really don't do this much because you don't really malloc much in C++. And then I think it's just delete data. We don't normally show this. But, oh, yep, delete needs to be delete array. It's a bit funny. Okay, so that's mallocing in C++. It's a little nicer, frankly. None of this casting, malloc, size, or whatever. You would kind of do it similarly if you wanted to just make an int. You'd say int I equals new int, like that. And then you could say delete I. That would be, there's basically an array version of mallocing and deleting in C++ and a non-array version. And the array version simply has the array brackets, surprise, surprise, and you need to give it a size because the array's of a certain size there as well. So it is a little bit more intuitive. But that's mallocing, that's putting stuff on the heap, freeing stuff off the heap. Same concept, different syntax, a little bit tighter, if that makes sense. You don't really have to do that much. I don't even think you have to do that at all in the course, which is why we don't normally cover it. But my point is, if you look at this slide, you'll see here it says, well, when someone constructs my vector, they'll give it a size, an initial size for the vector. And what we do is we set the size and the capacity at that initial size, but we also go and malloc a integer array of that size. And what does malloc return? Same thing in C++ as it does in C. It returns a pointer. Malloc returns a pointer because it creates unnamed memory over here and it gives you a pointer so you can reference something on the stack to point to it. It gives us that pointer and we store it here. So this would be like a constructor for our imaginary vector class. We have data pointing to our malloc array, then we have size and we have capacity. Now, that all makes sense. How would we have a destructor? Well, let's talk about destructors first in a bit more detail. Destructors are usually only really helpful when you have heap memory. Because if you think about everything we learned in classes back in week 3, when an object is destructed, the compiler is organized to go and systematically end the life of all of the object properties. It goes through it and calls the destructor of that. So there's like this recursive destructor chain that just handles everything. Basically, anything that is not a pointer is automatically handled by the compiler. So typically, destructors are empty things. You don't really implement them much. But where you do need to implement them is when your class, or the object of type class, is managing some heap memory, which this one is, right? Because we have our data that we're managing. So in this particular case, we would need a destructor to delete that data, right? So because when the actual vector class we're writing goes out of scope, the destructor needs to free that particular piece of data. Destructors are implicitly no except. Basically, what this means is like, you do not throw exceptions in destructors under any conditions. It's just not really how we program, is the idea that like you would have something like getting popped off the stack and it throws an exception. So that's just how, the one that we say implicitly, it's like they need to be no except. Not that that's a hard thing to do anyway, so it's not really a big deal.
Does that mean like post-destruction, or what about pre-destruction?
I don't understand what you mean by pre or post destruction.
Because you're saying when you delete it, and then you throw
So what I guess I'm saying is like, if you have a piece of code, and let's just imagine I've got like a standard vector of ints here, 1, 2, 3. Now, what happens if I just go and create a random scope here, right? Because we learned in week 3 that that's a scope. On line 15, this comes into scope. The standard vector's constructor is called. It will go and malloc it'll go and malloc 3 ints of space. And then on line 16, when it goes out of scope, the destructor for that is called, and the destructor for the int for the vector will have to go free up that malloced memory. All we're saying is that destruction process that happens when an object goes out of scope shouldn't and or can't ever throw an exception in there. Not that it should, because it's just deleting stuff. And if you think about it, I'm pretty sure free itself is also a no except function, because like if you try and free garbage, it just does nothing. Like if you ever remember from C, like if you just try and free some random pointer, it'll just be like, if it can't, it'll just be like, move on, kind of thing. So destructors are handy to free pointers, close files. There's also some other things around mutexes and OS-y kind of stuff, database transactions. But for the purposes of simple things, it's basically like you don't need to free memory unless it's a heap memory, and then you do need to free it. So if we look at back to this one, destructors are called on each member here. Sure, that's okay, because I always like to think about it like this. You got to remember, this vector, what is its, I mean, maybe not exactly literally. If you think about its actual size, it's got about 8 bytes. Look, as 8 bytes. How many bytes in an int? 8 bytes in an int, right? So it's like it's got 6 ints that it's managing, because, not quite int, but it's got 1 int for the capacity on the stack, 1 int for the size on the stack, then it's got an int pointer on the stack, and that pointer points to int on the heap. You know? And my point is, when you destruct this object, stack over here, heap over here, what happens is that the compiler knows how to get rid of the stack objects. It will pop capacity, size, pointer to data off the stack. But all this stuff sits here until we actually go and implement it and delete that data. And remember too, the compiler will remove the properties, the fields, after the destructor has been called. So when your particular vector gets destructed, first thing it will do is it will call the destructor that you wrote, which will free up these ints, free up the heap memory, delete it, and then after that will it go through and systematically pop everything off the stack. So that's how vector destructor, you could visualize, is done. Now we've just talked about destructor, but there are 4 others. We call them the rule of 5. When you write a class in general, you have to implement these 5 key things. Sometimes you can default them though, particularly if there's no, like if this is the cool part, if there's like no malloced memory in your class, generally speaking, you can default the copy constructor, copy assignment, move constructor, move assignment, because the compiler is capable of synthesizing those functions to just do the standard behavior with all the stack elements. That's why we haven't talked about them much when we deal with classes, because there's not much to talk about. But you do need to worry about these 5. We're going to talk about the 5 in a sec. This code is awfully small. We can't zoom in on this thing. You try and it just makes that, a little bit better. Okay, that'll do. What we're really trying to say here is like, you generally shouldn't define these yourselves if you can avoid it. So like a perfect class is one where you've gone and implemented them like this. And this is what a copy constructor, copy assignment, move constructor, move assignment looks like. A copy constructor, we've seen those before. It takes in a reference to a const type. And a copy assignment, we've seen those before. It's just the operator equals being overloaded. That takes in a reference to a const type and returns a reference to a type. A move and move assignment, we haven't talked about them much and we'll continue to talk about them, but they look basically identical. It's just there's no const on the input and there's a double ampersand to confuse the hell out of you, So the double ampersand we'll kind of come back to, but that's a little bit of the gist for now. This piece of code down here is a little bit bigger and a little easier to read. You go and create two vectors, short and long. You have just called the constructor. If you create a reference here from one vector to another, that doesn't call any of those 5 functions. If you say auto vector equals another vector without a reference, that's copy construction. Easily confused with copy assignment because there's an equals there. We've also talked about this before when it comes to, say, you have a vector like this one, auto s, and then you come along and you say, well, actually, I would like another vector of ints called p, which is going to be s. And you think, oh, that's copy assignment. And you know what? Copy construction, oh, that's a different thing. That would be like me saying this. Makes sense because I'm kind of, I'm calling the object, I'm constructing it. You can look it up in the CPP reference. But remember that this will be treated as a construction here just because P doesn't exist. There's nothing to assign. That's the most important thing to remember with assignment. To assign A to B, B needs to be fully constructed already existing. Whereas in this case, P is not here. So when you say, P equals S, P doesn't exist, so it has to be constructed. And this is important because if I was to, for instance, just change this up a little bit and say, P now that's copy assignment. Because on line 9, P is fully constructed by default construction, and then on line 10, it is copy assigned because P has been fully created and S is now kind of coming in and overriding certain things. So that's copy assignment. And then at the bottom ones here, you'll see, and copy assignment, very clear. Standard move, more magic down here. Now, standard move is a function in C++ that when you do copy assignments or copy constructions, it tells the compiler to call the move constructor or move assignment. How that does that's a little bit more complicated, but here, if I didn't have this standard move, it's just a copy constructor. But by wrapping what I'm trying to copy in the standard move, it just says, okay, actually call the move constructor instead. Call the move assignment instead. If you're not too sure what copy and move is, or if it's not super obvious, if we think about, maybe I can go to a simple class somewhere. Where were the classes? Yeah. Maybe I'll have to just... Doesn't really matter, but if I look at something like this, if you have a class and it has, I'll just actually look at what's on the slides. I think that was a little better up here, right? This particular class has 3 items, data size and capacity. That's just what we saw before. When you copy assign that, the compiler, what it has to do is it has to go and copy all that data across one by one. Now that by itself isn't terrible because you think it's just 3 ints, it'll be over in a flash. But what a move assignment and move constructor do is they actually just totally kind of dump it straight there. It's not copying it across. It's quite literally just replacing it. Now that's going to be some underlying magic going on in the computer where you could imagine, instead of copying data across, it's just changing what it references and stuff. And I don't know how to go that deep into it, but it's much more efficient because you're not having to actually, and you can imagine this may be easier if your object contains an array with 1,000 ints in it. If you have to copy all those 1,000 ints across, that's a lot of copy operations that has to be done. But if you can just move it, you're basically saying, hey compiler, this thing isn't pointing to whatever memory it was, it's now just pointing to that. So imagine it as some kind of deeper pointery mumbo jumbo going on where you can just reassign stuff, right? Yeah.
What happens if the
Well, the compiler wouldn't probably let you call something that goes out of scope. I'm not sure what you mean, maybe.
Like, so we have A equals supposed to move B.
Yep.
And then B goes out of scope.
After or before you move it?
After you move it.
So I think we get to it after, but once you move something, that thing you've moved is like, you just assume it's gone forever now.
Oh, okay. So
Yeah.
Once you move something, like, it's gone.
Yeah, I think the correct terminology is that once you move an object, it's in a valid but unspecified state, which basically means that you can still use it, but who the hell knows what's going to happen. It's kind of similar to undefined behavior. So once something is moved, it's just torched here. So in these cases, it would be bad programming practice to ever use vec long or vec short after you've done a standard.
It's moved to a new location, right? The data is moved to a new location, memory address.
Sorry, I've just lost my slide. What the hell did I click? I think I tapped on the bottom or something. Can you like jump? Oh, okay. Learn something every day. Yeah, I mean the data has been moved from the old object to the new object.
But the location of the memory location changes.
I don't know. Yeah, I just don't know how that actually goes on. Visually, how I want you to understand it is you've got object A over here. It's got some properties in it, like property 1, property 2, property 3. It's a funny face. And then you've got object 2 over here, which has the exact same thing. And naturally, the problem is if you copy assign it, what's going to happen is it's going to have to go through each property and move all that, send all that data across. But the equivalent of a move assignment is basically taking that and just going, loop. Now it's there. This thing is rubbish now. Don't touch it. You've destroyed it. And this thing was moved across really quickly without having to copy everything across.
What happens to the initial properties? Do they just get destructed each time before you move it? Is it destructed?
Yeah, they would get destructed. Yeah.
And then that implies that has to be the same type.
Yeah, exactly. Like you can only move the same type to itself. Yeah, it's not possible to do it any other way. Yep. Okay, I'm just going to go through a few of these here. So, firstly, vector copy constructor. If we look at this here, these are not my favorite slides to talk to. The copy constructor is written kind of as you'd expect. As you can see here, what happens is, let me just copy this. I'll just copy this. It'll be easier in the editor. No real surprises in this. Let me put it in something with syntax highlighting. So if I just kind of cut down on all this crap for a sec. Here's our imaginary vector that we wrote. Here's the copy constructor that we're going to have to implement here, as you'd expect. And this is us implementing it down the bottom. Now, what you do when you copy construct is pretty intuitive. You got to create a whole new array. You got to malloc a whole new thing. You're going to copy across the size, and you're going to copy across the capacity. One benefit of the copy is that, this particular, like you never think about this. If you copy a standard vector that has a bigger capacity than its size, someone at some point had to decide if you copy it, does it actually malloc the full capacity or just the size it needs, right? Because you could do either. In this case, we're just mallocing the size. So if we had like a 50 meg vector that had 100 meg of space, 50 meg of actual data with 100 meg of space, and you copy it, it'll copy it to be another 50 meg vector. I don't actually know if that's how it's done. I probably doubt that's how it's done. I don't know. Never really thought about that when we go through these slides. This is just meant to be an example of how someone might do it. You would usually assume that copying should copy it. Otherwise, you're just going to confuse someone at some point. So it probably doesn't do this would be my bet, but I don't know. So I copy it, but then I also have to copy the data across. Now, I could copy the data across by doing a C-style array for I equals 0, I less than the size, like do it one by one. Or I can use standard copy in this case, where I'm giving it a pointer. And this is the funny thing we never really talked about. We talk about how STL iterators are abstract notions of pointers. But what's cool is you can actually pass literal pointers into a lot of STL algorithms as well. And they will deal with them. So standard copy we've seen previously took in like a dot begin, and then it took in like a dot end, and then it took a dot begin of the new thing, right? So you basically said, here's the stuff I want to copy start, here's the stuff I want to copy end, and here's the start of where I want it to go to. And it would take that and it would copy it into that other thing. And we're actually doing the exact same thing here if you were to pause this or brain pause it and think about it. We're just doing the same thing with pointers. We're saying, yep, here's a pointer to my original malloc array. Here's a pointer to the end of my one past the end of my original malloc array. And then here's a pointer to the new malloc array. Can you do that copy for me? And what's nice about this is because you're using standard algorithms, people like you who might be C++ programmers are able to just kind of quickly read this and be like, oh, it's just a copy. You don't have to kind of see for loops and other kinds of stuff. You're just relying on existing semantics, which is very powerful.
Can you explain just that? I don't know if you explained in other classes, just to push that point.
Which point, sorry?
What's the point you're at right now? Like what it's actually defining there?
This? Yeah, that's the constructor initializer list. That one was from week 3, which I don't know if you were, did you see week 3?
No, I didn't see that. I was just
Okay. Yeah, it's basically the one where we can like shortcut the construction of these properties. Because it doesn't actually matter in this case because the default construction for these is trivial. But where it matters is if you more had like a more complicated type B. Because without the constructor initializer list, it will go and default construct it, and then if you initialize it in the body, it'll, you know. It's not really about scope. It's more that like the ordering of the construction is that the first thing it does is try to construct objects with the constructor initializer list, and then anything you didn't construct in the initializer list, it will go and default construct, and then it'll call the body. So if you don't construct anything in the initializer list, it will default construct, which most of the time is probably fine, but it might have a performance penalty depending on what you're trying to do, what the types are. For things like int, I doubt that default constructs. It probably just allocates the memory on the stack, and there's no like construction logic and cycles that you have to do. So copy constructor, pretty straightforward. Copy assignment, really, really similar. Just trying to have a look at what we got here. So what we've got here, I'm just going to replace the copy construction one. What did I miss there? So seems strange. I feel like there's something missing there. Let me just check. Standard swap's usually what we use for move. 2 seconds. Do we get to move? Yeah, I don't really get that. Let me come back to copy assignment. I'm not 100% convinced something hasn't gone wrong with the slide. It's not going to be too difficult though. Let me jump forward to R value, L values and R values. We've kind of teased these for a while in the course. I hate them. They're like the bane of my existence because they never make any sense. And the worst part is there's actually other types of values that we don't talk about in this course, like PR values and X values, which are types of R values. And I think someone very evil came up with all these names and ideas because it's very confusing. But an L value is an expression that is essentially in relation to a particular piece of memory. That's how I like to think about it. It always has a defined address in memory. And an R value is an expression that is not an L value. That's good. Generally has no storage associated with it. But there are tute questions where we kind of throw expressions at you and say L value or R value, guess, quick. And you have to guess. And I'm okay at it now because I kind of get it. But you got to think about expressions. Who's done compilers and programming languages, the course? Great. Hello up the back. Is it cozy up there? That's good. I'm not an expert in it, so I don't actually necessarily know the right answer. But how would you, if you still remember, define the difference between a statement and an expression? Yeah, I don't know. Yeah, however the language defines it. Yeah, exactly. I couldn't tell you, but what I can tell you is that typically, if you see something like this, that you would call a statement. I always think of a statement like a full kind of fat line of code before a semicolon. And again, that's a general rule and would vary on the language. Whereas things like this could be an expression. So you could take parts of the right-hand side or just the right-hand side, and that would be an expression, and maybe you have like a bigger statement. But generally, statements are made up of expressions. And you might think of this as a single line of code here. But if you actually break it up and think about parts of it, I here is an L value and 5 is an R value. Here, J is an L value and I is an L value. And the reason for that, and the really simple one to start you off with, is always going to be, does this thing have an address in memory? If the answer is no, it's probably an R value. If the answer is yes, it's probably an L value. So I, J, K, obviously all these variables, but 4 is an R value, doesn't have an address in memory. If I said to you, what's the address of 4? You'd be like, what? You know why it doesn't have an address? Because it's a literal number, and just like the string literals, it's actually embedded in the code, the binary code. It's just baked into that. You create some code that just has int I1 equals 1, int I2 equals 2, int I3 equals 3, right? And you just do that for like every number up to 1,000,000. You'll have a fat piece of code compiled, because it will go and put all those number literals typically in the compiled code. So a lot of those are going to be literals. And similarly, if you had another piece of code that said, like, as we saw before, const char star s equals Hayden, Hayden here is an R value. Because what address is that? I don't know. It's not really an address at all. And we also saw those cases when it came to the functions returning things. Remember the one where I said int blah, int I equals 5, return I? And then we called it here. We said blah, even if we just stand it out, see it. Blah here returns an R value, because you couldn't tell me where the address of that is, because it's kind of copied out. But if I was to change this to a reference, not that I should, to be clear, this would now be an L value that blah returns. All references are L values by virtue of the fact that references have to reference something else, right? So like they themselves reference something with a memory address. Pretty sure they're all L values. Okay. That's a simple enough idea, I think. L value references. There are multiple types of references, and I'm not going to spend too much time on a lot of these slides because they can get heady as well. L value references to const look like that. Once the L value reference goes out of scope, it still may be needed. Look, all that's really trying to say to you, all you really need to worry about is that references are generally L values, and sometimes when we refer to L value references, you'll see them in the format of the type with the ampersand after it. I think it's very academic. What is more important, though, is this new slide here with really small font. My goodness. Can I make it sort of bigger? Okay, we'll come back to that. R value references. When you want to reference an R value, you have to use the double ampersand. And an R value reference as an idea is very confusing. I still find it extremely confusing, and I wouldn't be surprised if you find it confusing. But this is simply saying my vec is a reference to something that is an R value and might not necessarily have a defined piece of memory, etc. You also don't really come across it too much. The reason we're talking about this is not because you're going to suddenly spend a lot of your life dealing with R value references. The reason is because move semantics, move construction, and move assignment, that syntax exists, and we need to talk about what that syntax is. So an R value reference, formal parameter just means a parameter of a function, right? This is a formal parameter here. Means that the value was disposable from the caller of the function. Right. So a person calls a function, they pass in something as a parameter, and when you take this as a parameter, what you're saying is that, yeah, whoever passed this in, it's something disposable, it might not have an address in memory, basically. You know, it might have gone out of scope, something like that. If outer, what's outer here? Outer modified value, who would care or notice? I don't think we need to worry too much about that. But let's have a look at this piece of code. So we have a main function. It calls outer with hello. Outer takes in an R value reference. Now this is interesting too, because I'm pretty sure, for instance, and I could be wrong here, if I copy that code for a second, fairly simple piece of code, a lot of crap came with that. If I simplify this down for a second, imagine I have a function called void outer standard string reference value. I just want to see if this one compiles. Oh, what have I standard string? Unused primitive value. Sure. Just let me rule out all the problems. No matching function call to outer. That doesn't make sense. Nah, I was hoping this might be illustrative, but the problem is that a string literal is not a standard string. A standard string is an STL class that instantiates an object that contains char stars underneath. A string literal is a char star. So what I'm trying to do here, I probably should have just done with an int, like this. Yeah, that's what I'm looking for. Function not viable expects an L value for the first argument. We're uncovering L value secrets now, right? So this is an R value. You can't pass it into a function that takes that by reference. You can pass it in by copy if you'd like to, right? We know how to copy stuff in. Been doing that since we were toddlers. But we can't pass it in as a reference because we can't capture that because it's not an L value. So all references are L values. However, what happens if I put the double ampersand there? It compiles. Now again, I don't want to pretend to be an expert in this because this is where my brain starts to dissolve. But this essentially allows us to take in references to R values. That's why we call it an R value reference. So no copying is happening here, but we are referencing an R value specifically. Again, I couldn't tell you the number of times that I've regularly written code and been like, oh my god, I need to capture that R value as a reference. But again, I don't write a lot of C++ code, so I don't want to poo-poo it. That's not the point. But if we look at this example more fully, that was just to get that point across. But let me just uncomment the code that we had here. So we have outer, we pass string in as an R value reference, and then we call inner, where we pass string in as an R value reference. Why does that fail?
Is it like kind of creating an L value by having that double ampersand?
Oh, we got a lot of stuff to include. This code wasn't really meant to be compiled. Oh yeah, this might be a bit of a bad example. We'll see how we go. Empty character constant. Oh, okay, that's why that was down there. Let's just not do that. No matching function called to inner. Oh, this is, yeah, expects an R value for the first argument.
Outer is sending 1 and you're catching. So the outer is catching it in string, you're sending 1 from here, integer.
Oh, yeah, right. What was the original example? Hello. I'm actually surprised it captured that. Yeah, I mean, like what's happening here is like, so we know that this is coming in as an R value reference, right? But then clearly if you look at this line here, function not viable expects an R value for the first argument. So inner expects an R value for the first argument, but we're not giving it an R value there, right? The caller has promised that it won't be used anymore. The caller has never made such a promise. R value reference parameter is an L value inside the function. Stuff is so stupid, honestly. There used to be so much of this in the course. I used to have to run shoots years ago where we'd like throw up all these examples and we'd be like, is this an R value or an L value? And everyone would get it wrong. And we'd be like, surprise. And no one understood what they were doing. So he's trimmed a lot of it out. It's relevant. I'm not trying to pretend it's not relevant because it's kind of core to the language, but it does very much bleed into. So I mentioned before, the origins of this course was it was a compilers heavy course. A few of you emailed me about that actually and been like, I like the look of the old C++ course. And it's become much more of an actual programming course. But this becomes an L value at this point. I'm not entirely sure why. I think it is explained here. Has been a while since I've like really gone super deep on a lot of this. But if outer value is modified, who would care or notice? No one. The caller main has promised that it won't be used anymore. So basically, because this is passing an R value, the caller is promising that it's not going to be used anymore. However, if inner modified the value, the caller outer has never made such a promise. Basically what it's saying is like, outer here has gotten this property and it has passed this through and not necessarily promised that it's never going to be modified. Because the idea of an R value is it's a reference to something. Because like if you think about it, a normal reference, like I have reference A over here and I give it to you, a reference, I pass that in. I still might need this. I'm like giving you temporary ability to play with it. But an R value, like a string literal or the return from a function or an int literal, when I pass that in, I'm not going to do anything with it anymore, strictly. Very, very weird. Let me keep moving on that for the moment, because R value references are a little weird. They do get a bit weirder, but the reason they're critical is to standard move, because standard move's implementation is a funny little thing. It's actually, I'm pretty sure it's something really close to this function here, where what it does is it takes in a value, something you would typically consider to be an L value, and it statically casts it to an R value reference. Following? Yeah. So it's not really, like it doesn't actually, the way to think about it is it doesn't strictly do anything, because when we look at copy constructors, and I can probably see this with standard vector. If I go to standard vector here, and we have a look at the copy, where's the constructors? Yeah, we have a look at the constructors. Notice here that we have a set of copy, these are all copy constructors here in some shape or form, and these are all, these are all copy constructors, and these are all move constructors down here. So I always like to think about it as it's a bit of a funny hack, because basically what a standard move function is designed to do is to simply typecast something so that you can match a different function. What I mean by that is, like, if I pass you a vector for construction and assignment, there's no way to actually specifically call a constructor and say I want this to be copied, right? There's obviously like some kind of crappy, crazy way where you could be like, I'm going to create a new standard vector of ints that's going to have a 1, 2, 3 in it, and then I'm going to create another standard vector of ints that's going to be copy constructed from A, right? But how does the compiler know if it should move or copy that? Well, you know, if you wanted to change the STL library, you could add like another parameter that's like true or false or something, or an enum that's like copy or move. You could add parameters to it, but that's not how it's done. How it's done is that A has a type, and A's type in this case is either going to be standard vector int reference, or it's going to be R value reference, right? And when we say reference, just to be clear, when we talk about L value references, every time we've used the word reference in the course so far, it has been an L value reference, because all references are L values, L value references are references. So this here is an L value reference, or what you might call reference, and this here is an R value reference. But the problem is, in both cases, whether you want to move or copy, it's the same thing you're passing in. You know, so how do we distinguish it? We literally just cast it to an R value reference type. It's just a typecast. I think this is why I found it so confusing, because it's not strictly obvious that that would be the way to go about that, but that is what is happening. You are literally just typecasting it to an R value reference. Move takes in a reference, typecasts it to an R value reference. It's still value, it's still the same thing, but it's a way to kind of, when you then pass it to a constructor or another function, to kind of tell it, no, don't copy it, go move it, because I'm an R value reference, I got typecasted to that, so go put me there. And then when we have a look at this piece of code, let's copy this in. Yep, so we call, what the hell happened to this one? Someone really ripped this one to shreds, it looks like. Oh, yeah, outer and inner. I'm not sure why that happened. So now what we do, we call outer with an R value, because hello, the string literal is an R value. We pass it in here. We know that works because we captured it as an R value reference. for reasons that again I couldn't explain to you in great detail, at this point in the function, anything else we do with it, it becomes an L value. So if we wanted to then pass it as another R value reference to something else, we would have to call standard move. Remember, every time you see standard move, all I want you to see is static cast R value reference. That's all standard move is. This particular piece of code is gobbledygook. It doesn't make a lot of sense. It's just kind of demonstrative. But the point is, if you wanted that previous piece of code, we had to compile, because at this point it was treated as an L value, which again, I don't actually know why. That's the one thing I've been talking about tonight. I couldn't tell you why that's the case. Because to me, intuitively, if this was an R value reference here, this should be an R value reference here, right? It's the same type. So it should work here fine. I don't know why it doesn't. Everything else I can explain. That one I can't right now.
If you pass in a R value reference like static cast hello and then pass it into inner, you could do the same thing?
Yeah. Yeah, I mean, like,
So it would say that's an L value, so if you do this, because that's what a steam move does, doesn't it?
what it's saying is when it tries to call this, it tries to pass in value as an L value, which...
But I'm saying when you do the static casting to a R value reference, the steam move's going to return that, and then it's going to be passed in inner. Right?
Yeah, it'll work. Yeah.
So that'll work.
Yeah, exactly. I mean, that's all standard move is. It's just that static cast.
So it's when you put it in the function, it considers an L value. Right, that's what
No, I guess so. It's more like value behaves in this function like an L value. I don't know why, but it is passed in as an R value reference. It's just if you then wanted to treat it as an R value reference, we have to use standard move. The main point I'm trying to get at with all this, and again, a lot of the detail doesn't really matter except the standard move part. Standard move typecast it to an R value reference. The reason that's useful, coming back to all of this, is that when we implement things like the move constructor, which I'll pull up here, right, let me get rid of a lot of this code again. Here's my move constructor. Get rid of the destructor too. This might be a move constructor where we're taking the original component, and this is a little hack that Chris used to put in, because his approach, which I always thought was interesting, because obviously what you could do here is you could then like try and standard move the original data and things like this, right? Like this makes sense. It's like it's a bit weird. But if I were to move an object, just like copying, right? If you want to move an object, like copy an object, you then copy the underlying properties. If you want to move an object, you just move the underlying stuff. So you could go and try and standard move a lot of this stuff across. However, one way Chris talked about doing it a lot was that standard exchange is basically, it's like a STL, I don't know if it's STL exactly. But it basically replaces the value of object with new value and returns the old value of object. It kind of just like literally swaps things. And what he was kind of doing with this was saying that, hey, what you do is, this is how you kind of leave the old object in a better state. Because like we said before, when you create a move constructor or move assignment, what you need to do is leave the old object in a state that's valid, but again, unspecified. The reason it needs to be valid is so that you actually need to kind of clear the data out, right? Like you as the person writing the move component of the object, the class, need to clear it out and put it somewhere else, and you need to leave it in some random state. So the random state in this case, if you've got like a pointer to an integer and two integers, the state would just be like a null pointer. Null pointer is just a C++ alias for that. So don't think of those two things as very different. And you leave it with like 0, 0. Because the other way you can do this, and I think I've seen this implemented like more thoroughly, will be someone's like, well, my data is standard move original data. And then they'll go and do the same thing for size and capacity. And then they'll be like, well, now the original data is equal to null pointer and the original size is equal to 0, right? Like if you weren't using the initializer list as well as the fancy stuff too, that is where your code would probably end up, which kind of makes a bit more sense at face value. You go move the 3 underlying things. Also, standard move, I don't know how standard move works for ints and stuff, but I imagine it just probably actually, I don't even know if standard move's quicker. I can't remember. Let me check. I'll check after the test. I don't know. But at the very least, it's an easy way to clear things out. Sometimes move can be quicker. In this particular case, I think maybe the better way to explain it is, what do you notice about this particular standard move? Is you'll notice that, and maybe let me kind of clarify some of my earlier comments. So earlier I said standard move makes things quicker because it goes and re-points how things, it goes and instead of having to copy all the memory across, it can just change where things point to. Yes, that's true, though if you have a class that is purely a couple of ints like that, and you standard move it, naturally what it's going to have to do is it's going to have to copy the data across and then clear out the old data. I made some comments about, well, it's going to do some funky stuff to speed that up. It's not going to speed up that part. That actual stack moving is just going to be moving, copying data across and leaving the old thing in a different state. The areas where it does speed up is this one, because what you notice about this is we didn't do another malloc at all here, right? So that process of mallocing and copying stuff across is way quicker. And what I mean by that is if you have a standard vector, right, and the vector has 1 million ints in it, if you do a standard copy, you're going to have to copy across the vector size int, its capacity int, and 1 million ints as well on the heap. If you do a standard move, what's going to happen? You're going to have to copy across the size and the capacity, but that's it, because you just change where the actual data points to. So you do see massive speed benefits there, because a natural thing sometimes is you might say, oh, I've got a variable A over here, I'll just copy it into variable B and get rid of A. It's sure, that's how you might program generally. But as C++ programmers trying to think about the performance of things, you'll generally want to toss away A, and you're well, if I don't need A anymore and I'm trying to move it over here, then I'll just actually move it and get the performance benefit of that. So I kind of implied earlier that you'll see some benefit to these stack properties with the moving, but it's not that. It's this part here. It's the fact that you don't have to move that heap object across. This one, my point is, this is Chris just doing some fairly concise writing, where basically what happens here is he's well, what this will do is this function this standard exchange, it'll take data, return it, and then set the original's data to null. Again, it depends. I find this stuff harder to read at the start, but that's just because I don't work with this every day too. If you're doing a lot of C++ code, you'll generally find this code written a lot cleaner because it's more concise and it's using standard idioms and things like that. It leaves very little room for things to be misunderstood or missing lines and stuff, right? You can't accidentally, in this case, you can't accidentally copy something across and not reset the state of the old thing because you've done it all in one line. That's why we use things like this. Do you have a question?
Yeah, so under the hood, would it be using standard move and be exactly the same as you showed before?
This one would just be copying, because the example I gave here, when you standard move a primitive type, I'm pretty certain it is just copying it. Right? And what I mean by that is if you have something just me freestyling code here, int a equals 5. If you say int b equals reference a, or you say int c equals 5, right? Same. This one here is copying a current variable. This one here is just setting it. You get the exact same result. So I'm pretty sure standard move on primitive just copies stuff. Oh, so the point of this was if you think about it intuitively, this is an L value and this is an R value. So if all you did was cast the L value to an R value, it's just the same outcome.
I was asking about the exchange, SD exchange. Under the hood, will it just do SD move again, or is it it's going to go?
I don't know, but I don't see why it would need to. Yeah, because it would just copy it. and maybe it'd move it. I don't think it would matter because it's just going to, whether it copies it or moves it, it's just going to, yeah. And again, I don't talk about this all the time. I haven't taught this course in 3 years, so I'm just trying to refine what I was saying earlier. Like, I think where you can fall down with standard move is, you know, the function itself does nothing. When you call standard move on something, it doesn't move anything. The thing that moves anything is the implementation of the move assignment and move constructor in the library that you're using. So when you call a vector, like when you have like a, you know, when you have standard vector auto a equals standard vector int 1, 2, 3, and then you say auto b equals standard move a. The calling of standard move doesn't move it. Calling of standard move typecasts it to an R value reference, and then at that point, once you've said now I'm move constructing it, it is the vector itself that has defined the move constructor to do that efficiently. And that's where you get the benefits from that.
Do you know standard swap? Like, what is the difference between exchange and swap?
So if I had to guess, I think exchange will return a value and standard swap will not return a value. I don't know. Yeah, so I guess pay attention to this. So standard swap takes in a type T and another type T. Yeah, it needs references. All these things kind of, well, they don't need references. But what this one's saying is like you take one reference and another and it'll swap the values of it, but it'll return nothing. What standard exchange does is it will take in 2 values. The second one can be an R value reference, and it returns something of the first type. And what I mean by that is if we look back at the code here, and we unwind and we go back to some of the stuff Chris wrote here. The point is that we actually need a return type of this, because like what standard exchange is doing the equivalent of is it's saying, imagine like if I was to write it here, exchange, just for ints or something, I'd say like int exchange, int original, int reference original, int reference new, or whatever. And I would say, well, sorry? No, you can't use the word new as a variable. So you would say, in this case, you'd say, well, like int temp equals original, and then you would say like original equals new, and then you'd like return temp or something like that. Yeah, I mean, sorry, that might not be the best, but my point is like, you maybe ignore that function. What it's actually doing here is it's saying, well, you're trying to exchange, the original data is the old one, the one you're trying to move from. And what you're saying is that I want that data from original into my new one, and then I want to set original to be null. So what it's doing is it's like capturing what the original data was, setting that to be null, and then returning the original data for our new structure. So that return is critical to the difference between exchange and swap. Because swap here wouldn't really, and you couldn't really swap either with this because swap needs 2 L values. The swap equivalent would be this data, right? Because that's what you're trying to do. You're trying to kind of swap the 2 datas. Because you're like I write here, I'm like a new object with no state, and there's my old object with all its state, and I want to take it and give it all my old state. But the problem you have with that is that at this point in the code, the old state, the new state doesn't exist yet. Like this data is not a valid thing yet because we're literally constructing it right now. So what I mean by that is like what you could do, for instance, if you wanted to do this another way, because I gave you that other one, is you could come along and you could say, well, my new data equals the original data. Or wait, sorry, you could say my new data is null, my new size is 0, and my new capacity is 0. Now obviously this isn't good because this is your new thing is empty and your old thing still has all the stuff, right? So what you would then do is you would say, well actually I'm going to standard swap it all. I'm going to swap this data and my original data, and then I do the same thing for size and capacity. So that's the other more obscure way of doing it, is but you first have to set up the state of what the new one is so that you can swap it with the old one. So now the old one has this kind of irrelevant empty state, and I have the new state. So what Chris wrote with the exchange one is just like, and again, the best code is the code that's understood. To smart people, maybe? I don't know. But here, this also works fine. Standard swap. Or you could do that other one I showed you where you just like set everything manually. The exchange the exchange relies on the fact that you have nothing to swap with yet because you haven't constructed the object. Oh, like none of it's really faster. Faster to write, yeah. The best code's the code that's written fast, I guess. It's like so the reason exchange is interesting here. I don't want to say what the best code is here because I don't think we have it in the best practices guide, and I don't think tutors would pin anyone on this like level of detail. And I don't even think any move constructors you write would have anywhere near this level of complexity. But the point is, the reason things like exchange are better is because by definition, it makes sure that you can't accidentally include only one of these lines. You can't define null and then swap it because, for you to call exchange, you have to have passed it 2 values. So it's a better programming practice because the structure will have a natural compile time check where it's looking after you more, in a sense. But if the code's valid, I wouldn't say one of them's particularly better than the other. C++ purists would probably like this one because it's using lots of abstractions and stuff, lightweight abstractions. They love lightweight abstractions. That's what C++ is built on. But yeah, I mean, in a pinch, I'd say this is better because you just can't like put the wrong thing in here, right? You can't forget to do that. It won't compile. So usually those things are good for that reason. It's the same with copy. Like the good thing about standard copy is it expects 3 things and you have to give it the 3 things it expects. Whereas a for loop, you can maybe forget a part or do the dot end wrong or something like that. So move assignment is really similar. I just want to highlight this one here too quickly because move assignment and move construction look nearly identical. If we just analyze the move assignment code here for a second, now we're using swap. And we're using swap, it makes sense because we've actually got 2 objects already existing. So we have things to swap in this case. So we swap everything across, and then we take the old stuff and we just start wiping it out. I don't think this line makes sense though now that I'm looking at it. Sorry? Yeah, it's more like I don't think, because you've swapped it. Yeah, okay, sure. Yeah, that makes sense. I get what it's saying. Yeah. So what it's saying here is like, if you have like old vector that has like an int with 100 items in it, and then you have your new vector which has int with 1,000 items in it, and then let's say you say old equals standard move new, right? You want to take your new vector and move it to the old. A lot of how we've been talking previously is like when you move something, you're actually moving it to an empty object, like an object with no state, like a blank canvas. But what we're saying is there's actually a lot of instances where you'll actually have 2 objects, not a lot of instances, but you'll have 2 objects. One of them has stuff in it and the other one has stuff in it. And when you try and move assign it, because when you copy assign something, you erase the old thing. So what we're saying is when you move assign, you erase the old thing too. But if you follow this approach where the way you move it is just by swapping everything, you have to kind of free this one, right? Because you don't need it anymore. The same would be true for copy assignment, I guess.
Why was deleting the original data? I just wanted to ask. Is it saying that if I defined it earlier, then I set this to be equal to that? Or expect that to delete a data misunderstanding? Because here's the operator setting to equal.
This is a move assignment. And what we're saying is that we basically have this, my object, that I'm trying to move something, assign it to me, and we have original. And we're trying to say, this should, I don't want to overload that. This should now become, or like original should now become this. That's what we're trying to achieve here. Original should now become this. Maybe if I write that the other way around.
So if you just say original equals this.
So I mean, in a code sense, if you just said this equals original, which is what you're trying to do, right? This would copy assign it. Because original is an object with a memory address, makes it an L value. L value will match the copy assignment. If I wrap this in standard move, it is now a move assignment because I've typecast my original object to an R value reference. Gets move assigned to the, this. Now this isn't real code here. This is just me explaining it. But the point is that naturally we want to keep the original stuff. We want to move that into the new thing. The reason we're deleting the original data here is because we've swapped it. You could obviously rewrite this as well and be like, I don't know if this wouldn't work. You could just delete the data straight up. Because if you're about to move something on top of you, you don't need what your data is anymore. You can malloc it, because it's like a new family's moving into your house. So you don't need your stuff. But I don't know why, if that's even bad.
So delete here is not actually getting rid of the memory or something.
Sorry?
Delete here is it ultimately just like remove it from wherever it's stored.
Delete's just freeing a malloc memory. Yeah, it's just freeing malloc memory.
Just write swap dereference from this and origin. I mean, you don't need to swap one by one. Just swap two objects.
You do need to swap the objects. Okay, so here's the really tricky thing. It's like if you don't implement this, right? If you just come along and you just say, you know what? I'm just going to default it. What a default will do is a default, if you just wrote that, a compiler will come along at compile time, and all it's going to do is it's just going to take these, and it is just going to do that, right? So when we say like you don't need to write them all out, surely, you normally don't, because the compiler will just do this magic for you. The problem is that because we have heap memory, this will have a problem. This will have a memory leak, more specifically, because all we're doing is like swapping pointers and then getting rid of, well, we're just moving it across, we're copying it across and then just forgetting about the old one, if that makes sense. No, that's all right. So like this is the default one, but that isn't good enough for us. So what we need to do is come in, and then what it will typically do with that then is it will, I don't know exactly, but it'll probably try and default these as well, potentially, to like their old point. But your question was around, do we really need to write all those swaps out, right? That was the question?
I mean, can you just write one swap?
Your question was like, can I actually just do something like standard swap, this and original in some way?
I think probably you should dereference this.
Yeah. Firstly, I don't know if that would be a reference because it is a pointer. So that in itself would probably. Oh yeah, no, it would pass it in. I mean, potentially. I don't know.
If you can do this over here, you can do this in any way. And then even if your variables are private, the heap swap is able to access it.
Maybe. I don't know. It's a great question. I'm sorry to the YouTubers. I'm kind of ignoring you just because we're running behind it a little. Let me jump back to, what was that piece of code we said we'd come back to before? It was this one, because this is what I'm thinking about, because you kind of mentioned this here. Because I have seen that kind of idiom before, where what will happen is that, because this was the other copy constructor, right? That came up. So this one's a copy constructor because it takes in an L value reference. This one's copy assignment, my bad. Words, very complicated. This one's a copy assignment. And yeah, you can see in this particular case that the way they've gone about it is simply to literally create a copy of it and then swap it, which I don't know why you need to swap it there. But yes, you can do this is the point. Like you were kind of asking that question around, can I swap whole objects? You can. The only times you have to be careful is like we couldn't obviously replace this whole thing with like a giant swap because, well, actually we could. We just then still need to actually deal with the data part, the malloc-ing thing that we'd missed, you know? Because like we still need to free that. That's a really important line. Yes, you can do that.
Then if the original object goes out of scope, then it should be automatically freed, right? If we swap it.
What do you mean by if the original object goes out of scope?
Because the original object is now swapped, and if the after return this after line 83.
The tricky part is like the original object still exists. You know, it like exists somewhere before this program. We just kind of cast it to an R value reference to pass it into this function, which again is, I think, just a weird way that language is written. The point is that we still need to do these things to clean it up because when we swap it, we're taking the thing over here we want to move on to us, and then we're moving all our garbage back out to it, right? But when you move something, the right thing to do is to leave it in like a valid default-ish state. So then we actually need to kind of clean it up as if we are not strictly destroying it, but I mean, we need to destroy any heap memory, but then we're just kind of resetting all the stack memory after it too. Move assignment, move constructors. There's a bunch of extra information on here. Move is an optimization on copying. The move from object is immutable. You can kind of read that if you'd like to. Explicitly deleted, copy and move. We may not want certain objects we write to be copyable or movable. There's a great example of that in... where'd it go? It's meant to be another lecture on smart pointers. Maybe it was meant to be today. We got actually tons of time in week 7. This is not going to take up 4 hours of lecturing. So we'll probably cover smart, and it's for assignment 3. There's another lecture we do on smart pointers, which is a really intelligent way to manage pointers because this is the thing. We know that pointers are bad, but we need them because the heap is managed by pointers. STD libraries use them. So we have this cool thing called smart pointers, which allow us to manage pointers in a really, really safe way that we will talk about in week 7, not needed till assignment 3. But some smart pointers actually don't want to be copied or moved. The idea of copying or moving particular smart pointers is bad, so they actually explicitly delete copy constructors or move constructors as well. So that's mainly just saying you can do that, just a heads up. Implicitly deleted, copy or move. Under certain conditions, the compiler will not generate copies or moves. The implicitly defined copy constructor calls the copy constructor member-wise. If one of its members doesn't have a copy constructor, the compiler can't generate one for you. So what we're saying now, this has nothing to do with L values and R values. It's kind of back to classes and things. If you don't, if you have a class and that class has member fields in it, you know, in our previous class it was an int star, an int, and an int. If those member fields can't themselves be copied or moved, we're saying the compiler won't go and generate an overall copy constructor for the class by itself for you. You'll actually have to explicitly define it. And last one, and this is a good point, if you define any of the rule of 5, any constructors, destructors, copy constructor, copy assignment, move constructor, move assignment, or destructor, it's good practice to either write them all out explicitly or to default and delete them all. So if you're writing a class, you should always at least have an explicit line for each once you define one of the 5, even if that line is just to write default or delete on that line too. This is a cool idea, but I actually think that's going to be a lot. These two things for me relate much more to smart pointers. So I'm going to kick those into the smart pointer lecture slides for when we talk about it next week. So yeah, we can kind of call it there. But just 1 minute. What I want to leave you with, because I know this is quite a heady lecture. It's my least favorite part of the course in general. What I want to leave you with is that in C++, because it's an efficient language, all a big summary, we don't just want to be able to copy things, we want to be able to move things. Moving is a process where we can say, well, actually, hey, if I've got a bunch of data here, I don't want to have to go and, one by one move it across. I just want to be able to kind of shove it over on this side. Particularly with heap objects, which is where a lot of the data is, because most of the space we have is on the heap. So that's where the big objects kind of rest. If you have a vector and a very big vector, it will typically have most of its memory on the heap. Standard moves away, moving is a way to do that. We distinguish between moving and copying via the type that is passed into the constructors or the assignments, and everything that's an object's typically an L value. So if we ever want to do a move, the way we tell the compiler that we're trying to move something is simply by casting it to these R-value reference types that we talked about, where R-value references are non-const things with the double ampersand after it. So standard move is a cast that helps the compiler know which assignment or which assignment or which constructor to call. And all that tells is the library writer, which might be you, which one of these to call. And when you implement your standard move or construction, you can do so in a way that makes sense for your type. An important reminder, most of the copying or moving doesn't need to be explicitly defined unless you're dealing with heap memory or some other kind of weird thing like a live database transaction or something that has overhead. But maybe a better way of saying it is not that you need to do copy and move if you're dealing with heap objects. A better way to say it is that if all you're doing in your class is storing a bunch of stack properties, whether they're pointers or whatever else, but they're all just stack, there's no stars or anything weird, then you can probably just skip a lot of this and just define things as default, 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 default. Any last questions before we wrap up? Well, that was fun, wasn't it? Cool.